What if I put a minus tan h x minus 1 here? Okay, this is two tan h's, one on the left, one on the right, and they're sort of canceling each other out on both ends, so they're only bulging in the middle, right? Now if I pull them apart a little bit more, you'll start to see that this very Gaussian-like appearance is really just kind of fake. Oops. All right, I can make them as stretched out as I want to. And I could flip this one if I wanted to, and then it would go up and then up again. And you're kind of seeing that I could piece together any two S shapes. If I have an S-shaped curve, I could make another S. I could take two S's and concatenate them together in any way I like, right? Okay. So next, let us consider a model that consists of several units in this form, such that I have x and y and for now, just for intuition's sake, let's pretend that x is just a scalar, it's not a vector, y is just a scalar too. I'm going to make the bold claim that this model can compute anything. And by anything, I mean any function you could possibly imagine that involves one input and one output. And I'm also going to say that these 6 units in the middle represent an unspecified number of units. So I may add more units if needed. But given that much leeway, will you accept that this model can approximate anything with arbitrary precision? Let's challenge it. So let's suppose you want it to come up here and then jump down here and then go up there and then down here, and then what else can we do with our data? That's crazy. We'll go up here and then have it go straight for a while, and then have an unsampled space, and then come up here and then drop down there. And I mean, what else can we do that's ridiculous? And then we'll go off to infinity up here, and then we'll drop way down to 1 times 10 to the negative 38. And I mean, that's about as crazy of a function as you could imagine representing in data, isn't it? Okay. Well, remember how I can take my S shapes and I can stitch them together to make any shape that I want? Well, I'm just about to underwhelm you with not impressed. Sounds like a thing that Iago would say on Return of Jafar or something like that. Okay. Imagine an S shape that connects those 2 points. And then imagine another S shape connecting these 2 points. Let's see. Okay, that's not a very good S shape. In fact, let me change colors here. So this is kind of actually continuing on forever because that's what tan H does, right? But then I'm going to take another S and connect it to there, and it'll continue on forever this way. But whatever those constant things do in adding together, we'll just take care of it by adjusting the bias value to compensate. You see how we can do that? And then I could take another S shape and connect from this point to there. My hand is not steady, I apologize. But if I have enough S shapes, I could basically fit one between every pair of points, and it doesn't really matter how tall my points are apart, because if they were really tall, I could just scale my tan H here, right? Like that tan H could become a 2 tan H. And that 2 could become a 3 tan H. And I could make this tan H stretch as far as I want by simply adjusting that scalar that factor that multiplies by it, right? So I can, okay, let me put it this way. Here is a single tan H. I can shift it left and right by adjusting this value inside of the parentheses. I can stretch it up and down by adjusting this value that it's multiplied by. And I can raise it and lower it by adding or subtracting. Whoa, what did I do? From the tanh thing, right? That's pretty obvious. I can stretch it this way and pull it that way and shift it this way and shift it that way. Okay, so if I can shift my S shapes anywhere I want, I could certainly fit them between all of my data points. And do I even need to keep going? I think you can tell that I could make a model that perfectly nails every single one of these points, and no matter how wonky you made them, I'll perfectly fit them, and I will say, wah ha ha, my model fits your points. I have a universal model that can fit any data you could possibly throw at it. Okay, now let me come back to this. What's that?
You can do like all sorts of real analysis type functions that computers can't handle. You know, like indicator functions of rational, indicator functions of irrational.
Yeah, so I mean, obviously, if you're doing parity, for example, if you're taking the line of all the natural numbers and you're asking the question, what is the last bit? This function is going to go up and down and up and down and up and down and up and down at every single number on the number line. And now in order to perfectly fit it using this approach that I just said, I would need 1 unit for every stinking data point. And yeah, that's going to be a completely practically worthless neural network. What I'm showing you is purely theory only right now. So I should put on my theory hat. This is my theory hat. Yes, this is completely impractical, but what I'm about to show you assumes we have an infinite amount of memory and a Turing machine and plenty of time to implement it. Okay, now I'm going to claim that this weight right here that feeds in basically scales the input that goes into that node. Do you see that? In fact, let's write the equation for this whole thing. It's going to come out to y is equal to tan h of wx plus b. Some weight times that plus b. Right? This is what it would be if there were only one hidden unit, because y has its own bias, and there's a bias on each of these hidden units. And so we're going to take x, we're going to scale it by the weight, add the bias to it, run it through the tan h function, scale it by this weight, add the bias to it, and there you go. Well, look at what we've got. This b right here basically takes your output and shifts it up or down. So this will raise or lower the S shape, however we wanted. Now look at what's inside of here. This b right here will slide the S shape left or right. Does it not? Because that's what I just did in my graphing program. And this w right here will stretch the S horizontally because it's scaling what feeds into that tan h. And this w right here will stretch that S shape vertically. So we can stretch it vertically, we can translate it vertically, we can stretch it horizontally, we can translate it horizontally, all by adjusting this weight and this weight, which I haven't even put a W there for, and this bias and that bias. Okay. Well, essentially this model that I've drawn here, where a line represents a linear layer and a circle, this row of circles represent, or column of circles represents the nonlinearity. So let me say that a little more clearly. This is a linear layer, like you've implemented in assignment 1. This is a nonlinear layer, like you're about to implement in assignment 2. This is yet another linear layer. If you build a model that contains 2 linear layers and 1 nonlinearity layer, this model by itself is sufficient to perfectly fit any data you could possibly throw at it, given that you're allowed to change the size of the hidden layer to whatever the heck you want it to be. And it can fit the data perfectly, and therefore no more complicated model than this is needed for anything at all, ever, in the universe, period. Something like that, okay? You can come up with a really hard problem, but at least in theory, this model's good enough. And you might say, well, wait, I don't want 99% accuracy. I want 99.9999999% accuracy. Can you do it? In theory, yeah, because you can hit every point with precision. So any data you could imagine, this can fit. And that's all good and well until we ask this question. Is being a universal function approximator, also sometimes called an arbitrary function approximator, because this is a model that can fit with arbitrary precision to an arbitrary function that you can represent in data. Is that a good property or a bad property? Okay, so, well, the answer, of course, is yes. It's nice to know that we don't need to make neural networks more complicated, isn't it? I mean, if you wanted to study machine learning and you wanted to come up with a model that was sufficient to handle your problem, you might ask the question, are neural networks good enough to handle my problem? In theory, the answer is always yes, because there's nothing they can't do given enough hidden units, and if you have 3 layers. In practice, the answers might be a little different, but we're playing in theory land right now. But this would tell you, if you were thinking to yourself, I came up with a new idea to make neural networks more flexible. How would we respond to that? What dumb research. Neural networks are already sufficiently flexible to fit anything, right? So therefore, if you make a neural network more flexible, that's not really good. In fact, interestingly, most of the work in making neural networks better involves making them more rigid, making them less bendy and less able to handle any problem that you can imagine. And that tends to make them yield better results. Isn't that interesting? So it's good to know that yes, whatever problem you've got, a neural network can fit it with arbitrary precision, given some assumptions. But it's a really bad property to have if you don't need it. Let me demonstrate. Let's suppose our data goes like this. Bink, 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 bink. And I want to know what happens. I'll add some axes so you feel like this is a plot. What happens over in this region? Let's suppose that the horizontal axis is time, and the vertical axis is y, whatever the heck y means. And I want to know, indicate green to mean right now. And I'd really like to predict the future. Where's y going? Now, any rational human is going to say, obviously it's going up, so bing, 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 right? You'd predict something like that. Is that true? We don't know, right? I mean, it's quite possible that the function just happens to go like this. Isn't it? I mean, is this a valid function? Sure. In fact, anything is a valid function. It could go up and then down, and then it could go up and then down, and then up and then up and up and then down. This could be the future. Another possible future is that it could go up a little bit more and then plunge and then climb and then do a loop-de-loop. Just kidding. That's impossible. Time now doesn't do that. There's no way to know the future. There's only ways to predict the future. What's the difference between knowing something and predicting something? Well, if you've observed it, you know it. If you haven't observed it, you're predicting. That's pretty reasonable, I think. So now let's ask the question, how do you make a prediction? Well, you make a model, and then you see what the model says. So for example, let's suppose our model looks like that because we know how to implement OLS and we have a linear model. Do you think this model will make good predictions? Just relying on my human intuition, I will say, yeah, that's probably pretty good. Right? It's probably going to go like that. Is it going to be exactly like that? Well, this model doesn't even perfectly fit the training data. See, everything left of the green line is training, everything right of the green line is test, right? Because I'm doing time series prediction. Well, if it doesn't even fit the training data, you can be sure it's not going to fit the test data better than it fits the training data. And by sure, I mean probabilistically sure. It might. You'll never know for sure it doesn't until it happens, but odds are pretty good it's not going to fit any better than the training data. It might go like this. You might be seeing a trend that's just about to take off, right? Or you might be witnessing something that's going to plunge. But as far as we know, given this data, and of course this is assuming a few things. This assumes that this data is fully representative of everything that is known. Is it possible to have knowledge outside of your data? Sure, of course it's possible. But we're going to make the assumption now, and this assumption is a pretty big assumption, so make sure you keep this in mind, that the data, these points represent everything that has ever been observed, ever. Meaning this is everything we know about the universe, this is everything that is known. All of the sum of human knowledge is represented in these points. If that's the case, then we really can't make a better prediction than to just assume that maybe a linear model is what the future will hold. Would you agree with that? Okay, well, some guy comes along and says, I have a better model. My model goes like this. Oops, I missed. Oh, dang it. Ah, I erased it. Okay, his model goes like this. Sound effects are really important. Okay, person A and person B both make predictions. We'll call them person red and person green. Whose predictions would you put money on? I would invest in the red person. I mean, assuming I had money and was forced to invest in one of these two things. I would put my money on the red model. Why? Well, it's simpler. So Occam's razor, right? Don't multiply complexity beyond necessity. Isn't that what Occam's razor says? Okay, we better check it out. Occam's razor.